Hey everyone, and welcome. So, you've probably heard the word algorithm thrown around a lot, right? But what does it actually mean? For a minute, let's forget all the complicated code. Today, we're going to break down algorithms into what they really are, a powerful and surprisingly human way to think and solve problems.
Let me ask you something. Imagine I gave you a gigantic, heavy dictionary and told you to find the word serendipity. How would you do it? Seriously. Would you start at the very first page and just flip through one by one? Or would you be a bit cleverer? Maybe crack it open somewhere in the middle, see what letter you're on, and then decide which half to search next. Go on, think about it for a sec. What's your move?
You got a plan? Well, guess what? That whole step-by-step process you just cooked up in your head, that's an algorithm. See? You've been using them your entire life, probably without ever calling them that. Okay, so now that we've got the basic idea, let's actually make it official. We're going from just a feeling to a solid definition, because this is really the foundation for understanding how computers think. At its absolute core, an algorithm is just a recipe. That's it, a list of step-by-step instructions to get something done. I mean, think about it. The steps to make your morning coffee? That's an algorithm. The directions your GPS spits out? Yep, another algorithm. They're the instruction manuals for, well, for everything.
But, coming up with a good algorithm, that takes a special kind of mindset. In the programming world, they call it computational thinking, and it's really built on three big ideas. First up, we have something called abstraction, and really, it's just the art of ignoring stuff. It's all about zeroing in on what's absolutely essential for the task at hand and tuning out all the other distracting noise. Okay, think about your car's sat-nav, right? It tells you exactly what you need to know. Turn left in 200 feet. It doesn't bother explaining the complex physics of orbital satellites or signal triangulation. It completely hides all that crazy complexity so you can just focus on one thing, not missing your turn. That's abstraction in a nutshell. All right, next up is decomposition. So if abstraction is about seeing the big picture by ignoring the details, decomposition is kind of the opposite. It's all about taking a huge, scary problem and just chopping it up into smaller, much more manageable, bite-sized pieces. For instance, let's say you want to sort a giant list of numbers. That sounds kind of big, right? But using decomposition, you'd break it down. You'd ask, okay, first, how do I just compare two numbers? Then, how do I swap them if they're in the wrong order? And finally, how do I just repeat that process for the whole list? See? Suddenly, that big, scary problem feels totally doable. And that brings us to the final piece of the puzzle, algorithmic thinking. This is really where the magic happens. It's the part where you take those simplified, chopped-up problems and you write the actual recipe. The clear, step-by-step instructions that will solve each little piece, and ultimately, the whole thing. Okay, so a programmer's thought through the problem, they've broken it down, what's next? Well, before they write a single line of actual computer code, they draw up a blueprint. And they usually use one of two main tools for this. On one hand, you've got pseudocode. It looks a lot like code, but it's written in plain English, so you can map out the logic without worrying about syntax. On the other hand, you have flowcharts. These are visual diagrams with boxes and arrows that show the flow of decisions. They're awesome for visualizing how everything connects, especially when you've got a lot of if this, then that choices. All right, that's enough of the high-level stuff. Let's get our hands dirty and see some of these algorithms in the wild. We're going to start with one of the most common tasks there is, finding something in a list. So let's look at two totally different ways to find something, linear search and binary search. And remember that dictionary problem from the beginning? Well, this is basically the start at page 1 method versus the split it in half method. As you can see, they have some pretty important differences. First, we've got linear search. And honestly, it's about as straightforward as it gets. You could call it the brute force method. It literally starts at the very first item in the list and asks, hey, are you what I'm looking for? If the answer's no, no big deal. It just shrugs and moves on to the next one, and the next, and the one after that. It just plods along until it either finds the target or gets to the end of the list. Simple, for sure, but you can imagine on a really long list, this can get painfully slow. Okay, now for the clever one, binary search. This is our divide and conquer dictionary trick. But remember, it has one huge rule. The list has to be sorted first. If it is, its first move is brilliant. It jumps right to the exact middle of the list. And right there, it asks a simple question. Is the thing I'm looking for bigger or smaller than this middle item? And bam, based on the answer, it throws away half the entire list. Gone. It just keeps doing that. Chop in half, check the middle, chop in half again, and it finds the answer with insane speed.
So that raises a question, right? How do we get a list sorted in the first place so we can use something amazing like binary search? Well, one of the classic ways is called bubble sort. It works by looking at two items right next to each other. If they're in the wrong order, it just swaps them.
It just keeps doing this compare and swap shuffle all the way down the line. By the time it's done one full pass, the biggest item has literally bubbled up to the very end, right where it belongs. Then it just does the whole thing over again and again until everything is perfectly sorted.
So it's pretty obvious that binary search is way, way faster than linear search, right? But how much faster? This brings us to one of the most important ideas in all of computer science: the race for efficiency.
And this chart, wow, this chart says it all. Look at linear search. The more items you have, the longer it takes. It's a straight, predictable line. Double the items, you pretty much double the time. Makes sense. But then you look at binary search, that line is practically flat. You can throw a massive list at it, and the time it takes barely even budges. This right here is why your search engine feels instant and a bad app feels clunky. The difference isn't just big, it's astronomical.
So, what's the big takeaway from all this? It's that there's almost never a single best algorithm for everything. It's always a game of trade-offs. Yeah, binary search is a speed demon, but you have to do the prep work of sorting the list first. Linear search is slow, but it's super simple and works on any messy, unsorted list you throw at it. Choosing the right algorithm is all about understanding the problem you're actually trying to solve.
And that leaves us with one last thing to chew on. In a world that is completely obsessed with speed, if faster is always better, why on earth do these simple, slower algorithms even exist? Why not just use the fastest one every single time? What's the hidden power in being just good enough? It's a trade-off that's definitely worth thinking about.